Good morning. So, myself, Dr. Polash Nakui, Associate Professor, Department of Chemistry, SI Ministry of Science and Technology, Chennai. So, today I'll be discussing about coordination chemistry, which is very useful for BSc first year students who are pursuing chemistry, as well as BTech first semester students who are studying different aspects of engineering. So, what is coordination chemistry? So, we know that coordination basically that metal and ligand they will be interacting with each other. So, in fact, this coordination chemistry it is very much known from the beginning of modern chemistry. We all of us know about the Prussian blue that Ap4, APCN6. Why it is a Prussian blue color? It is. And to define their color it is we need to study that why this color it is. Okay, so in 1893 Alfred Warner he got the first Nobel Prize in 1913, and he has told about this coordination chemistry part. Okay, so even that blue vitriol copper sulfate pentahydrate, even though it's a blue, but what about anhydrous? Why it is colorless? Or why copper iodide is colorless? So you can see in this case Prussian blue used as a pigment. So these are the colors. So coordination chemistry basically involving the transition metal complexes. Transition metal means first scandium to zinc, that is a first order transition element 3D. Similar we have 4D, 5D elements are there. So basically they are having d orbital is there. So when they have electronic transitions will be there, either ligand to metal, then because of that dd orbital transitions, that electrons will be absorbed, means translated from lower energy orbital to higher energy orbitals, and as a result when it go back it will give the color. So we'll discuss in details. So first of all let me talk about Warner's theory. Warner's theory was very much famous because he has given the concept of two valency. Primary valency means oxidation state of the metal ion. Secondary valence means how many number of ligands attached to the metal ion. So for example, um, so basically coordination number it can be 2, 3, 4, 5, 6, 7, 8 up to 12, more than that. Whereas primary valency it can be plus 2, plus 3, plus 4, plus 5, plus 6, plus 7 is possible. Now, before talking about primary valency and secondary valency, first let's discuss about ligands. What are called the ligands? So ligands basically may be neutral molecules or negative charge. So they should have lone pair ability, and it will try to give the electron donor capacity, maybe leave space to the metal ions. For example, you can see water, ammonia, chloride ions or cyanide ions. So coordination and coordination geometry. Suppose you have two coordination. So if metal is attached with two ligands, so it's a linear structure. You can see AgNH3 hold to plus chloride ions, or AgNH3 hold to plus nitrate. So in this case, silver is a positive charge, so oxidation number primary valence is 1 and secondary valence is 2. That's why it's a linear structure. When you talk about copper Cn3 2 minus, so here cyanide is a minus 3, so copper will be plus 1 charge, and it's a, as 3 ligands are there it will be forming a trigonal planar Ml3 sp3 hybridized. Now when you talk about coordination 4, that means 4 ligands are involved. You can see cobalt tetrachloride, COCl4 2 minus. So in this case, cobalt having +2, it's a primary valency, and 4 chlorine atom is there, it's a secondary valency. Similarly, when you talk about MnO4 2 minus, so MnO4 2 minus means oxygen is each having -2, so it will have -8. So it will be manganese is +6. +6 oxidation number means primary valency, and oxide ions acts as a ligand. So basically, it will be forming tetrahedron complex. Now, Ml4, you have square planar complex also it is possible when it's a DsP2 hybridization tetrahedron complex sp3 and square planar complex it will be DsP2. So in that case, you can have D8 electronic configuration, for example, nickel, NiCN4 2 minus, or we can have cis platinum complexes. They are square planar complexes. Now, if we talk about coordinate number 5, so 5 valency will be there, 5 ligands will be there. You can see manganese. Manganese is a neutral molecule 3d5 4s2, and it is bound with the 5 covalent, 5 coordination, 5 ligands are there. So in this case, Mn2 plus is your oxidation number or primary valency, and 5 ligands are there, and that should be 5 MnCO5 or Ml5. Similarly, when you talk about octahedron complex, say sp3d2, by the way, this is square pyramidal or trigonal bipyramidal will be sp3d. Now, for octahedron complexes, you have CONH3 whole 6 3 plus. Ammonia is a neutral ligand, so that means cobalt will be +3 charge. It's a primary valency. Ammonia is a neutral ligand, so you can have basically sp3d2 geometry. So similarly, we can have 7, 8, 9, 10, 11, 12, all these geometry is possible. It will be a little bit more complex. So you can see basically octahedron geometry, it's sp3 geometry, sp3d2, trigonal pyramid prism, it's sp3d geometry. Then we can have this kind of different geometry will be there. We'll discuss in details. So let's come back to the ligand again. So ligand can be bidentate ligand also is possible, monodentate ligand also possible, polydentate also possible. So bidentate ligand means it has denticity 2, means two way it can bind with the metal ion. So for example, oxalate. Oxalate to carboxylate, it can bind with the calcium ion, and that's why calcium oxalate is formed. Similarly, ethylene diamine. Ethylene diamine, it can bind with the metal ions, so it has two donating capacity. Another case, you can see the ruthenium. Ruthenium, it is a octahedron complex. It is bind with the ammonia, 5 ammonia, and it's a pyrazine compound. So it's a bidentate ligand, basically. Now, polydentate ligands, first of all, monodentate ligand, it has bounding capacity 1, bidentate 2, for you can see bipyridine, orthophenanthroline, oxalate carbonate, and polydentate ligand. This is very much important because it is useful for chelate complex. What is chelate complex? Basically, ligand will make the complex or surround the metal ion in such a way that it will form the cyclic structure. It's just like the octopus. When octopus that go for the hunting, with its 8 hands or legs, they will capture that whole that hunting that animal. So that's a kind of cyclic structure, ring structure. So in this case, we can see dimethyl triamine. You can have 3 biodenticity. Similarly, triphosphate ions, you can have 1, 2, 3, 4 multidentate. Similarly, when you talk about ethylene diamine tetraacetate ion, which is a hexadentate ligand because there are 2 nitrogen and 4 carboxylates, so it can easily form complex with calcium or magnesium ions. So chelate basically that when ligand may complex with the metal ions forming a cyclic structure, so that's called chelate complex. You can see that metal when calcium or magnesium ion or cobalt ions form complex with EDTA, and it is forming this octahedron complex. So this is also called as an octopus. So Let's talk about isomerism in coordination compounds. So similar to organic compounds, the same formula you can arrange in different way. So you can have isomers. So these isomers, it can have different bonding, different properties. So for example, structural isomers. So it has ionization isomer, hydrate isomer, coordination isomers, linkage isomers. And then stereoisomers, basically three-dimensional projection, you can have geometrical isomer or optical isomers. Now let's have one example of ionization, hydrate, coordination, and linkage isomer. So what is ionization isomer? So basically that composition will be same, but their positions can be different. Ligands can be either inner sphere or outer sphere. You can see chromium NH2O5 SO4, it is in the inner sphere and bromide in the outer sphere. And when the bromide is inner sphere, sulfate is outer sphere. So basically, if this is your cationic part and bromide is your anionic part, this is your cationic part, sulfate is anionic part. So that means their anions are defined, and that's what is called ionization isomer. If you talk about hydrate isomers, it's just presence of water molecule, whether present in the inner or outer sphere, you can have different isomer. You can see that you can have CrH2 whole 6 Cl3. It's a violet color. CrH2 whole 5 Cl, Cl2 water, it's a green color. CrH2 whole 4 Cl2 Cl water, this is also green color. So you can see different color can exist based on the position of the water molecules. And that coordination isomer is another case where the metals, two metals will be involved in the complex cationic part and anionic part, and when these metals will be exchanging their ligands, they can be called isomers. So you can see CO NH3 whole 6 here CN6, where cobalt is connected with ammonia. In this case, cobalt is connected to cyanide and chromium is connected with ammonium. So that's a just exchange. So that's called the coordination complexes. And what is linkage isomers? Linkage isomers basically depends upon the ligand. So when a ligand will have same ligand, but it can connectivity in different way. For example, NO2 minus, it can bind with the nitrogen to the cobalt, or it can bind with the oxygen. So when it is bind with the nitrogen, this color is orange color. When it bind with the oxygen, its color is brownish color. So that means the same ligand but donating site is different, and that's why it's called linkage isomers. You can see that SCN cyanide or isothianate cyanide in SCAs. We can call this is a violet color and this is a something different color. Now, let's talk about stereoisomers. So stereoisomers basically on a three-dimensional projections, how they behave. Okay. So for example, square planar complexes. In a square planar complexes, that angle between these ligands, it will be 90 degrees. So it can have when uh, MA3B, we cannot get any geometrical isomer. Geometrical isomers means when two ligands are in the same side, they can be called cis. When two ligands are in opposite side, they can be called trans. So for a MA2B2 complexes, this is your cis isomer, this is your cis isomer and trans isomer when they are in opposite side. Similarly, well-known example is the cisplatin and transplatin. Cisplatin, two ammonia group in the same sides, that's a cisplatin, and trans, it is there in opposite sides. In fact, just for information, cisplatin having anti-cancer activities, whereas trans isomers, it exhibit comparatively useful pharmacological effect, but they are not used as a cancer. So basically, different isomers having different properties. Now, in a octagon complexes, how this geometrical isomer is possible? In this case, again, the cis-trans isomer is possible. You can see if it is MA5P, either it can have in a perpendicular to the plane or it can have in the plane structure. Or when you have two ligands are opposite, suppose MA4 D2 B2. So you can have cis isomer When two ligands are in the same site, that's called the cis isomer. When they are in opposite side, they can be called trans isomer. So you can see that CONH34 whole 2 Cl. So when chlorines are on the same plane, that is called cis. When they are in opposite plane, opposite side, they are called trans. And based on that, you can see cis form is a red color, green, and trans form is a green color. But again, another option is there. It's called that octaton complexes MA3B3. So here you can have facial and meridional. So facial means when three ligands are successive to each other, irrespective of whether it is on the plane or on the perpendicular. So that is called facial. And when they are in 1 to 4 position, that called the meridional. So that's a different concept. So now let's come back to stereoisomerism. Stereoisomerism, one is your geometrical isomers, another is your stereoisomers. So what is stereoisomers? Optical isomers, sorry. Optical isomers, basically it should be chiral compounds, and they should when passed through plane polarized light, it will show optical activity. So optical activity to appear, so basically molecule has to be chiral, and they should be non-superimposable mirror image isomers. But enantiomers are basically non-superimposable mirror image isomers. So you can see that hands of human beings, they are non-superimposable mirror image isomers. So what is plane polarized light? Plane polarized light, basically the normal light when you pass through plane polarizer, all this light direction, it will be in one direction. Okay, so unpolarized light means in any direction the light will move, electromagnetic radiation will move. When it passes through plane polarized light, all this will be in the same direction. So basically nickel prism is used to obtain plane polarized light. Now when a chiral molecules, when a light will pass through that chiral molecules, depending upon that chiral molecules can rotate the plane polarized light either a clockwise direction or anti-clockwise direction. If the chiral compound rotate plane polarized light in a clockwise direction, then compound will be called dextrorotatory, or if it rotates in a anti-clockwise direction, that can be called levorotatory, D or L. Okay. Now in a enantiomers, basically it's a mirror image isomers, but and they will have similar physical and chemical properties. In fact, two enantiomers, it will rotate the plane polarized light in completely opposite direction, in opposite, I can tell it's a opposite magnitude. Suppose if one enantiomer rotates the light in a 32 degree in right side, that's a dextrorotatory. Others will rotate 32 degree in the left side, that means the levorotatory. But in case you have 1:1 enantiomer, that's called the racemic mixture, and in that case optical rotation will be 0. So for example, COEN2Cl2 Cl exhibit whether a geometrical isomer. Yes, it is possible that chlorine fluorine opposite side and ethylene diamine bidentate ligand, so it is called trans, and this is called uh, also trans. Mirror image isomer, right? Identical, superimposable. So they are optically inactive, trans isomer. But if you go for the cis isomers, you see here if the chlorines are on the plane, then ethylene groups, they are in one side. You can see if you just put the mirror image, they are not they are not identical, or they are not superimposable. So in that case, these cis isomers are called optically active. Similarly, if we go for ethylene diamine or oxalate or one thing phenanthrolene case, so they are showing when they used to bind with the metal ion, so they are showing optical activity. For example, cobalt 3 oxalate or iron 3 oxalate, they are uh, basically mirror images are not identical or non-superimposable, and that's why they are called optically active. So now come back to the common concept that how metal ligands bonding will be there in a coordination compound. So mainly these are the theories people have talked about much early. So valence bond theory, it was developed by Linus Pauling in 1930s. Crystal field theory was proposed by Hans Bethe in 1929, and ligand field theory of molecular orbital divided by Van Blake, Mulliken and Hund. And in fact, Linus Pauling got Nobel Prize two times in 1954 and 1962. Bethe got Nobel Prize in 1967 and Beck got Nobel Prize in 1977. So what is valence bond theory? Valence bond theory talks about sharing of electron, explain the geometry of the complex. It can talk about magnetic properties of the many magnetic properties of the complexes. But so it's basically sharing of electrons. It needs the Lewis base, and you need the Lewis acids, for example, metal ions, and they can form coordination bond. Now, central metal ions, it will provide the s, p, and d orbital, vacant s, p, and d orbitals, and accordingly, it will decide what kind of coordination will be there based on the ligand, number of ligands. So each ligand, it will share at least one sigma orbital will be there, and it should have the lone pair ability. An empty orbital of the metal atom or ions, they will go hybridizations to form the same number of hybrid orbitals. And using valence bond theory, one can predict what is the geometry of the complex. Even magnetic properties also can be possible. For example, if you have sp hybridization is linear, sp2 means trigonal planar, sp3 means tetrahedron, dsp2 is square planar, d2 sp3 or sp3 d2 octahedron, dsp3 it's a trigonal bipyramid, or dsp3 also square pyramid also possible. Or last one not least, sp3d2, it's octahedron complex. Now, what is the limitation of valence bond theory? Valence bond theory, main problem is that it cannot explain whether a complex is low spin complex or high spin complex in case of tetrahedron or octahedron complex. It cannot tell about the color properties, why a certain metal complexes is colored. So that's why that concept of crystal field theory comes. What is crystal field theory? So basically, crystal field theory, it can talk about color, it can be explained about magnetic properties, it can talk about stability of the oxidation state, it can talk about lattice energy and so on. For example, iron hexahydrate, it's an octahedron complex, green blue complex. Titanium hexahydrate, it's a violet paramagnetic compound. Cobalt hexaamine, it's a yellow diamagnetic substance, like this. So crystal field theory is based on the concept that when negative charges of the ligand approaches the metal ion, positively charged ion, there will be a repulsion will be there between the d electron present in the metal complex, and there will be degeneracy will be created. So definitely, there is some postulates has been talked about. So ligands should be considered as a point charges. Interaction between ligand and metal will be electrostatic. Here, metal will be positive charge or neutral charges. So whenever that metal ions will be there, all d orbital electrons are degenerate. But when ligand is approached, these degeneracy will be lost. Okay, so it will have certain barycenter. Barycenter means when the ligand is approached to metal ion, energy level of the d orbitals, it will go up, and that's called the barycenter. Now there are two options is there out of the 5d orbital, that orbitals which is along the axis dx square minus y square and dz square, it will be quite different compared to orbitals in between the axes. That means xy, dyz and dzx. So in presence of the ligand, when complex formation will be there, that time that d orbital splitting will be there, and it will be created T2G orbital, that means the components in between the axis, and EG orbital, that is along the axis. And you can see there are 5 d orbitals which are dxy in between the axis, dyz in between the axis, dxz in between the axis, whereas dx square minus y square along the x and y axis and dz square is along the z axis orbitals are there. Now, this is the common case how can explain in a octagon complex. So, in a octagon complex, it has a d orbitals, and that's called the barycenter. In a barycenter, d orbitals will be elevated in terms of energy. Now, you see there is a splitting will be there where dxy, dyz, and dzx it will have much lower energy compared to dz square and dx square. And the energy gap between the T2G and EG, that is called your crystal field stabilization energy. So generally dx square minus y square and dz square, they will contribute zero point 0.6 equivalent of that crystal field stabilization energy each electron, whereas T2G orbitals they will contribute each minus 4 delta O. And overall the gap is called CFSE, crystal field stabilization energy. So you can easily explain this part. Basically, this is your d orbitals when there is no ligand is there. In presence of ligand, this they will elevated to the higher energy level, and after that d orbital splitting will be there. So energy gap between this T2G and EG, that's called that crystal field stabilization energy, that is delta O, and that maximum energy is 10 dq. Now, in a tetragon complex, that scenario will be opposite because dx square minus y square and dz square orbitals on the metal ions, they will be in between the axis, and dxy, dyz, dzx, they will be towards the ligand. So as a result, its splitting will be completely opposite, that dz square, dx square will go down, whereas dxy, dyz, dzx, they will be go up. But although that energy gap between T2 and E, so here the energy gap will be 4 by 9 of delta O. Because in a tetragon complex 4 ligands are there, in a octagon complex 6 ligands are there. So as it is in octagon complex, CFSE, crystal phase stabilization energy, it will be higher compared to tetragon complex. So basically, if it is an octagon complex where T2G orbitals will be in the down, EG orbital going up, whereas in a tetragon complex, T2G will be, T2 will be in the up, and uh, E orbitals will be in the down. So definitely the energy gap between T2G and EG will be higher in a octagon complex compared to uh, tetragon complex. Now, when to expect tetragon geometry? So basically, if the ligands are large, there will be avoid ligands repulsions will be there. So in that case, crystal field stabilization energy can be applicable. So CFSE D0, D5, and D10, you can see here MnO4 minus, FeCl4 minus, zinc chloride, they can form tetragon complex. And if you talk about metal ion with small crystal field stabilization energy D2 or D7, their electrons will be in the lower energy. Now, tetragon splitting, that as the energy will be very high, they will favor the pairing energy because that energy group will be high. So electrons will try to fill up in the lower orbital than in the higher orbitals. So you can see that what are the factors affecting that magnitude of crystal field stabilization energy. First of all, higher oxidation state, it will have higher crystal field stabilization energy. In this case, iron 3 plus, cobalt 3 plus, cobalt 2 plus, and iron 2 plus. You can see iron 3 plus having the highest crystal field stabilization energy. Similarly, when you have group elements will be there, higher atomic number or higher d or f orbitals, it will have more crystal precipitation energy. So iridium. Then always octaton complex will have higher crystal precipitation energy than the tetraton complexes. You can see cobalt NH3 whole 6 2 plus, its octaton complex much higher energy than cobalt 2 NH3 whole 4. And the last one, not the least, ligands can be arranged in a spectrochemical series according to their ability to proceed with the increase in delta value, crystal precipitation energy. You can see that cyanide or carbon monoxide having the highest donating capacity compared to ammonia or electronegative atoms. So crystal precipitation energy depends upon the ligand strength. Higher ligand strength, it will have higher crystal precipitation energy. For example, in this case, cobalt 3, 13,000. This cobalt 3, 15,060. Then these are the things. So basically, cyanides, if you have, it is having high, strong ligand, strong crystal precipitation energy. So this is a spectrochemical series where carbon monoxide, cyanide, triphenyl phosphine, nitro, 1,10-phenolphthalein, ethylene diamines. So basically they are strong field ligand, whereas iodide, bromide, cyanide, chloride, fluoride, they are called weak field ligand. And this is the best example where fluoride is a weak field ligand, and that's why it's a lower energy orbitals, whereas water is a weak field ligand. You can see there are 3 electrons will be there, cobalt 3 plus. And then you have chromium ammonium whole 6, or you can see chromium 3 plus with 3d3 system. So with increasing fluoride to water to ammonia to cyanide, you can see that electron negative charge, or basically it has better strength ligand. Now different ligands on same metal gives different color. For example, copper pentahydrate, say blue color, but hexaamino copper complex, it's a blue color. It's a light blue to blue color. So how to calculate crystal field stabilization energy? That you need to multiply minus zero point 0.4 into T2G orbital electrons plus 6.6 into how many number of electrons is there in the EG orbitals. So for example, for D1 crystal field stabilization energy, it will be 0.4 negative. Hello. D2 is at zero point 0.8, D3 it's a 1.2. And there's a rule is there, so when you have more, how much value is there, at 1 delta O is equal to 243 kilojoule per mole. Hence the complex is stable. Similarly, we can see for crystal crystallization for the D7, sorry, D4 high spin complex and D6, D4 low spin complex, their crystal crystallization will be different. So basically large splitting, it will be having low spin complexes or kind of pairing energy will be involved, and smaller delta O, it is having high spin complex. So we can have two examples where cobalt hexacyanide is square planar complexes, where cobalt hexafluoride is a high spin paramagnetic complex. So high spin, low spin and pairing energy, when pairing energy is greater than delta O, the configuration T2G3 G1 is a preferred, this known as weak field. And when that delta O is greater than P, that means it will have strong field ligand. It will have more pairing energy. So accordingly, you can calculate D1, D2, D3, D4, D5, D6, D7, D8, D9, D10. You can calculate how many number of unpaired electron is there, and accordingly, you can calculate the magnetic moment. root over n into n plus 2. So square planar complexes are different still. You can see octahedron complexes, distorted octahedron, and this is square planar complex. In a octahedron complex, you can have T2G orbitals and you can have TG orbitals. Now, magnetic properties. Magnetic wave properties basically how a complex can attract the magnets basically, or iron metals, and then how they can be separated. So here spin only formula, you can have root over n into n plus 2, n is the number of unpaired electrons, so you can calculate whether a compound is a paramagnetic or diamagnetic. So if it is a spin only effective, so you can have root over n into n plus 2. So for your titanium 3 plus, it's a D1 system 1.73. Vanadium 2 plus, D2 system 2.83. Vanadium chromium 3 plus, D3 3.87. So like this. And it is matching with the theoretical value. And then we have magnetic properties. You can see K2COCl4. You can have 3 unpaired electron. When we talk about delta T means crystal crystallization as a tetraton complex. Whereas if you go for high spin complex, you can have 3 unpaired electrons. So basically, here also you can get magnetic moment close to 4. So number of unpaired electrons is 3. Same for both the state, and that's why both are parametric substance. And what is charge transfer complex? Basically, intense color come from the charge transfer complex. Basically, DD transition. Electrons will move from uh, ligand to the most accepted metal ions. Here you can see potassium permanganate. It's a purple color. Potassium chromate, yellowish color, and potassium chloride is a white color, and potassium dichromate is the again orange color. So that's the color coming from that negative charge of the ligand to the positive charge of the metal ion. So what are the advantages or disadvantages of crystal field theory? It can explain the color property, it can explain the magnetic aspects without knowing the hybridization. So it can talk about the ligands as a strong and weak field ligand, and it explains anomalies in physical property of the metal complex. And what are the disadvantages? Disadvantage, it does not explain why uh, carbon monoxide, although neutral, is a very strong field ligand, not the cyanide ligand. So that's all about my